science at Brown University, and he's published extensively in computer graphics and computer vision, and has done a lot of exciting research related to AR, VR, and robotic telepresence. So I think we're all looking forward to his talk today on differentiable rendering for scene reconstruction and VR teleoperation. And I really just want to thank James for coming to talk with us today. So thank you, and yeah, please take it away.
Thanks, Eric, for the kind introduction. I'm not sure, really, I'm in the room in which you can say I've done lots of work on VR teleoperation. I had a slide right at the beginning, which is the classic I'm not in my own domain slide. Our field has been struggling with this problem for years. Struggle no more. Computer graphics is here to solve it with algorithms. Right, and then 6 months later, right? Oh, that was actually really hard. Okay, and I was also a little bit intimidated. I was like, wow, the roboticists are serious people, right? They know, what am I going to possibly tell them, right? And then I looked through the schedule and I saw all these great pieces of work about teleoperation, about foveated rendering, marker tracking, and I thought, okay, it's fine. These are my people. We're going to be okay. We're going to be okay. All right, so a quick introduction about me. This is how I see the world. I have some kind of graphical synthesis algorithm, right? And that's going to turn some visual scene model into images of the world, right? And potentially the large scale. And then I'm going to have some analysis algorithm. That's my computer vision, right? And these form this, in principle, virtuous cycle, right? And if I can do good graphics and I can do good analysis, then I've sort of set up a visual Turing test where I can validate my outputs and my inputs, right? And then the human being sits on the right-hand side and they get to apply their creativity and understanding through perception, visualization, and interaction, right? A bit more formally, we have rays of light in space in all directions. This is what we call the planoptic function, all light. And cameras capture that and project this down to two-dimensional planes, which is the bane of my life because I've lost all of that directional, positional information a lot of the time. And then we want to recover by analysis these models, these visual scene models of geometry and lighting and things like material, also quite useful. And then higher level tasks like semantic information that we also want to capture, right? And then synthesis produces again from those models some two-dimensional representation that I then spit out on some display, and that goes over to the user. And in our case, that display is a VR headset or an AR headset, some mixed reality interface, right? My day-to-day is dealing with multi-camera systems. Right? Some of these are the kinds of systems we use in robotics too. I'm going to highlight the LiDAR here on the iPhone, the modern iPhones, because we're going to talk about LiDAR in the second half of the talk. But generally, the problem is how do I take this information and turn it into something useful for scene reconstruction to be able to estimate the three-dimensional geometry of the scene so that I can use that for localization and mapping. And then I can also use that in the visualization for the user. Okay. So then the problem is, how do I solve this analysis problem? How do I go from camera back to model? And typically the computer vision community struggled a lot with this, partly because there was no good way to use our computer graphics algorithms in a backwards sense, right? And that made it hard to integrate computer graphics algorithms into optimization frameworks that could help us recover these meshes, this lighting, this material, right? And in the past 4 or 5 years, partly due to things like auto-differentiation within frameworks like PyTorch and TensorFlow, and partly because of the fact that graphics people are running out of things to do, we developed this whole new set of differentiable rendering techniques. Okay, so I want to be able to perform my analysis task in the backwards direction to present gradients to some optimization problem that will allow me to converge on a solution. And typically this is quite hard. Lots of functions within the rendering process are not actually differentiable. The biggest one of these is called occlusion. Whenever I have one thing in front of another, what happens is that I get effectively a delta function, which is non-differentiable. Occlusion is non-differentiable. Okay, so that's the setting, right? In the past 4 or 5 years, we have now developed a set of alternative algorithms for doing computer graphics in reverse, for doing differentiable rendering. So here's an example. I have some teapot, Utah teapot, the most classic computer graphics example, and I have some initialization of where I think the teapot is. Right? And in this case, I have a particular triangle drawing algorithm called a rasterizer, and I can exploit some differentiable rasterizer to optimize the pose of the teapot such that it matches this target image. And this is only done through the differences in the pixel intensities between the target and the current version within the optimization. So this is already very powerful. And the explicit form of the render function is important, but ultimately we have some input, we have some rendered representation at each time step in our optimization, and then we have this clever function R that is going to differentiate them. And then I throw that into PyTorch, and off I go. It's immediately useful for things like pose estimation, as long as I know what the object is I'm looking for. Okay, but you have to be really careful how you solve one of these differentiable rendering problems. Here's a target in 2D, and I'm going to start with the same teapot, and I pose the problem where I get to freely move these vertices around. And the output transformation of this teapot into a square in my 2D plane is correct, but produces this kind of weird, junky space of shape. Okay. In your techniques, you may have heard of a few different approaches, right? And I'll just quickly cover these. I talk about differentiable rendering as if it's this like slightly softer version of classical rendering, right? And there are very expensive methods of rendering in a differentiable way, like ray tracing, what we call path tracing, right? And they take days and days. Okay. And then we have this thing that everybody's hyper excited about, neural fields, using multi-layer perceptrons to approximate some continuous value varying over space and time. Right? And they're also very powerful, and so we'll talk a bit about these. And then we have the things that people have mostly been using in the past few years, which are these like image-to-image style pix-to-pix you might have heard of, where I take a CNN and I have an autoencoder and I produce out an output based on some learning-based approach, right? And all of these, in some sense, are some kind of differentiable rendering. And from the right-hand side over to the left-hand side, we come to like more and more exact or more and more precise. Okay, so that's the setting, right? We have differentiable rendering, and it's allowing us now to solve problems in computer vision in a three-dimensional way that we didn't really have mechanisms to solve before. And it's vastly increased the quality of scene reconstruction that we can do. It just happens to be quite expensive. Okay, so then today I want to talk about two specific problems. I said I'd talk about scene reconstruction and then also about VR teleop. And these, we'll actually do them in reverse. We're going to talk about VR teleoperation first. And this is a project about how to use a multi-camera system and a simple differentiable rendering approach to remove the vestibular-ocular mismatch in VR systems. And then we'll talk about LiDAR, like I mentioned, using some neural fields-based methods. This is called TURF. And here we integrate time of flight and RGB sensors to try to produce better scene reconstructions. And in principle, this is what you want on the front of all of your robots. Okay. Everybody with me? Any questions at this point? Okay, so one of the core problems when we want to do VR teleoperation is how we show the world in the robot's point of view to the user in the virtual reality headset. Right? I'm going to blame Stephanie Telex, and partly I'm going to blame Eric Rosen for me studying this field at all. Okay, because a few years ago, and I guess David Whitney owes some blame as well. A few years ago, they were doing things like this. Right? I have my Baxter, and my Baxter's got a Connect 2 on it, a time of flight sensor. And this is, I think this is David in the headset, right? And I render a point cloud, and I've got the URDF rendered robot overlaid, right? And I've got even like these little camera views from the wrist mounted cameras. And as a graphics person, I looked at this and said, yeah, it looks okay. But it's kind of a bit jumbled, a bit messy. Can we do something slightly better? Can we do something slightly better? And Steffi said, yeah, go on, do it then. And so that was it. I was hooked. When we think about the different ways in which we want to teleoperate robots, right? Sometimes we think about egocentric application. Right? This is a classic early model of the telesystems system that's now being used in the Model T is being used in stores in Japan. So I try to match the camera systems on my robot to the display systems on the headset, and then as the user moves their head in the VR headset, the robot does exactly the same thing, and I hope that there's a one-to-one match between the two systems, right? But it's very difficult to build this kind of system in practice because human beings are incredibly nimble. We want this kind of one-to-one mapping between the human and the robot, but it's very, very difficult to get the robot to be able to match the human's range of motion, and also their speed of motion, right? So I'm a graphics person. I said, well, no problem. Let's just put a 360 camera on the top of the robot, right? It turns out you've already all done that. So I went back to the drawing board. Let's reconsider the camera system that we actually just saw. They look a bit like this, right? When you build a 360 camera system, typically you can't physically fit a camera that looks in all directions in a particular point. And so you build multiple different cameras on the same system, right? As a vision person, as long as you have any world point being imaged by any two cameras, you can do stereo reconstruction, right? So typically most multi-camera systems provide you with an ability to do stereo reconstruction. Okay, so then now I can provide some stereoscopic reconstruction cues if I can use these two images of every world point to synthesize a scene, right? Okay, question, a straw poll. I want little hands. I want to see hands, right? Has anybody ever looked at any stereo 360 like images or video? Anybody seen them in a VR headset? I see lots of shaking your heads. I actually see one hand. Okay, I see a few, right? A few, right? Okay. My impression of this stuff is that it sucks. Like it's bad, right? In principle, yeah, it provides me with binocular disparity cues, but in practice, actually, it can be significantly worse than just looking at a mono 360 image. Right? Actually, getting correct disparity from one of these camera systems is quite hard. Disparity is wrong whenever your head is pitched incorrectly from horizontal, which is quite often. It's wrong whenever your head rolls, which is also quite often, especially when you're looking at things in a confused state. And then disparity is undefined at the poles, right? If I look up or down, or if my robot itself is rotating with respect to the environment, then disparity is wrong. And I get headaches. I look at this stuff and I get headaches. Right? Okay, last thing. Why is everybody sitting down? Well, this is because of motion parallax, right? Motion parallax says I need to be able to translate my head in each direction too, as well as rotate, right? And actually, any head motion is a translation. I never rotate my eyes exactly around the optical center of each one. It's physically impossible. I have a neck. My head is joined at the back of my neck, right? And every time I rotate my head in any direction, I am also translating my eyeballs, right? So I'm also screwed there. What we really want is what you call 6-off. Right? I want 360 in any direction. I want binocular stereo. I want motion parallax. Right? This is easy in computer graphics. I just point my virtual camera where I want to see. This is hard in computer vision because I need an all-around reconstruction everywhere. Right? I'm going to show you the difference between these two approaches. Let's see. All right, on the left-hand side, thanks PowerPoint, is the version that doesn't have any parallax. You see that the chair doesn't move in relation to the background in any way, as me in the VR headset looking very dapper moves around, right? This is what causes sickness, by the way. So my ears tell me that I'm doing something and my eyes tell me that I'm not, or in fact, the opposite. All right, so here's what comes out of our system. So as I move my head in translation, right, I then see correct motion parallax. If you look at the corner of the scene there, right, it looks kind of smooth, right? And the headset motion matches the scene motion. You see the little occlusion effect there from the thermostat. Right? Okay, so the project takes 360 stereo camera footage and turns it into this 6-off representation. Typically, this is really expensive, right? Everybody knows that to do good reconstruction for real-time applications, this needs to run fast. So the next trick is how we actually do it fast. We're going to turn to, of all people, Disney for inspiration. Okay. Parallax. When you think of motion parallax, think of old animation films where the character is running against a background in the background, right? And I'm trying to estimate the scene depth of things to be able to give this parallax effect. How was this produced in the old animations? Well, I would physically build a set of glass plates that I would paint, or I would put transparency over. And then I would gear the different plates such that they moved at different rates, induced different disparities, based on how far away things were meant to be in depth. And then the camera rolls, and then I turn my crank, and I get this nice effect. Think of this as a set of images that have RGB and some transparency value, and I am integrating a long array into the camera, the different color and transparency values. Okay. We're going to take this idea and apply it to 360 environments. So now what we have is what's called not a multi-plane image, but a multi-sphere image. Okay. So I have spheres, sets of spheres that each have RGB and alpha surrounding the user, right? And the user's camera in the VR headset is going to freely move sort of inside the bounds of this inner sphere, right? And content that's far away is going to have in front of it all of these different sphere planes that are transparent, right? And content that's close is going to have opacity on one of the front spheres, right? So why is this, excuse me, why is this a good representation? Well, all I need to store are a set of images, one for each layer, which is RGB plus alpha. Okay? And I can apply a very cheap convolutional neural network-based approach because this is just one big block of memory, right? I just have pixels. I have pixels at different depths, but I just have pixels. Okay, we call this Matryoshka because it takes this omnidirectional stereo format, and the shells within shells are like a bunch of Russian dolls. So you might be thinking, well, okay, this is like some weird pseudo scene representation. where I have stuff at different depths, different opacities, different RGBs. Can I actually do something like pull depth back? How far away is stuff? Right? So this is what one of the depth maps looks like from this representation. If you ignore the color and you just integrate out the transparency, then you get something that looks like a depth reconstruction. Okay. The nice thing about this is that you can run it basically at frame rate. Because it's all just CNNs, it runs very fast. So we can have this running on video that streams. Okay, here's how it works. It's a learning-based approach. Okay, because it needs to be very fast. It needs to train these CNNs. It's a learning-based approach. So I start with my input video from the camera, which gives me a left and a right 360 image. We can talk about why that's weird later on. And then I downsample them because that's just a hell of a lot of pixels and I can't really deal with all that at once. I do my classic like stereo reconstruction sphere sweep volumes. I have some neural network that takes in these inputs, right? And then it's going to spit out these layers of color in the multi-sphere image, and then these layers of alpha, right? And then a little trick that we do is instead of directly estimating the color that gets associated with each of these spheres, actually we just estimate how much of the left view and the right view to blend together at any particular point. And that means that we can then sort of upsample, use the low resolution blending weights, upsample them, and use the high res video on top. Okay, so that's it. So we have some synthetic training data that we generate. We train this big system to render using a differentiable rendering approach, this set of spheres, right? And what you get out is something that looks a bit like this. What I'm showing you now is a particular real world scene with the method running, okay? And the camera is moving through the scene, right? And you see things moving about, and you see the parallax that's induced from the camera motion, except this is all virtual camera motion, right? The 360 camera itself is fixed in place in the middle of the motion, and all of this is virtual camera motion. So your robot gets to be wherever it is, right? And then we induce this representation that allows the user a sufficient, what you call headbox, to be able to see something plausible at each of these locations and avoid the fixed view that the robot has. If you were just doing like depth map reconstruction instead of this multi-sphere image representation, this is the thing at the top here, right? And the quality is a little better. So you see that on the right-hand side there at the top, there's this kind of stretching that happens. So I take my depth map, I mesh my depth map, classic approach, and then I re-render it. But there's nothing in the part where the mesh is stretched. This is an occluded region, right? And in our approach, we have somehow learned to put something behind the thing in front and produce a slightly nicer image. Okay, of course it's not perfect. What happens when you move your head outside that center sphere that I talked about? Well, you reveal what's behind the curtain, and you start to see these like sets of shells that you see at the bottom there, right? And because we have to reduce the size quite a lot, the resolution is going to struggle with data structures, right? So it's not perfect, but it works okay. It works okay. If you want some fast way to generate 6 degree of freedom VR rendering from a stereo 360 camera that you put on top of your robot, this is a reasonable approach to do. There's no pre-processing. It's fast enough as long as you've got the compute, which we can talk about afterwards. And so you can use it for things like, in principle, you can use it for things like robot telehealth. We had a go at this. Okay, here's the camera that we were all just looking at, this stereo camera. We had a go at this and had a little late-breaking work paper at VAM-HRI last year. And I'm happy to talk about that with anybody afterwards to see how that went. Okay, I realize I am fast moving out of time, but are there any questions at this point before we move on to the next?
Yes, I have a quick question.
Shoot, Matt.
So just a clarification question.
Yeah.
So there are there are a series of these spheres that you build up. How do you choose? Presumably you have to make a choice about how many spheres and how they are spaced relative to each other.
That's exactly
right. Is that learned, or?
It could be learned. There are other techniques that try and learn what the depths should be. You can think of this from a signal processing perspective, where you want to reduce aliasing, and that governs a certain distance that they must be placed away from each other. And the number of them you also want to also define strictly from an aliasing perspective. We use 32, and it's okay. It's okay for near stuff. You lose a bit of precision, but it's sufficient to provide you that sense of motion parallax that reduces the sickness that you would otherwise feel. But it's not great for like hyperreal rendering. So Google have a similar kind of system where they use 256 planes and a different optimizer, and it takes like a day per frame, and so there's all of these different trade-offs that come here.
Thank you.
Okay. All right, so then let's talk about how we can use differentiable rendering systems for improving the fundamental observations that we make using time-of-flight cameras. So most robots will use some kind of time-of-flight, either sparse or dense, using like LiDAR or a depth camera to be able to do SLAM, something like that. And this is work that is motivated by time-of-flight sensors that are now on smartphones, but in principle will work also for the kinds of sensors that we use on robots. Okay, I'm going to start off by just showing you like what kinds of errors we're used to seeing in time-of-flight images. Okay, these come from just a regular off-the-shelf time-of-flight camera, and we've imaged some natural scenes, right, from the perspective of somebody who was holding a smartphone, right? So anytime there's low reflectivity in the scene when it's dark, time-of-flight tends to give very bad results. Okay, lots of noise makes it hard to make predictions about what to do. Anytime there's anything reflective in the environment, I also have incorrect noisy estimates. Right? Time-of-flight works by sending light out into the scene and then measuring how long or how much of it comes back into the camera. Right? And if light bounces more times, it's going to screw up my estimates. Right? These are called multipath interference effects. Right? The other problem we have is what we call phase wrapping. So for LiDAR with the laser, typically the pulse goes out and comes back, and there's no particular problem with range, right? Which is why I can use them on cars outdoors, for instance. But things like a connector Azure is a slightly different way of producing depth, and it has a limited range. It sends out this sinusoidal amplitude modulated intensity and measures the phase shift of the returning light. And that means that the range is bounded by one of the wavelengths of the light that goes out. And so you get these effects called phase wrapping. You see this very, very bright region on the right-hand side, right, where the camera thinks it's really close to the camera, but actually it's not. It's all the way in the back, right? And it's because of this phase wrapping on the expected light, which makes them very difficult to use in practice, because how do you know when you've phase wrapped or not, right? Is the object I'm going to bump into right there, or is it actually 10 meters away? Okay, and so we're going to try and fix these problems using differentiable rendering. So here's what we can produce as our output. So the noise is mostly gone. It's much smoother reconstruction. Most of the multipath interference effects now provide at least the true path length rather than this noisy, incorrect estimate. And then the phase wrapping is fixed as well. Okay, so actually, these aren't the input camera views either. These are re-renderings based on the provided depth that's recovered from the method from a null viewpoint. Okay, so what you're seeing is the sort of accuracy, in some sense, of the depth through this null view rendering too. Okay, so how do we go from these noisy, kind of bad time of flight estimates to these somewhat better time of flight estimates. This is where we introduce this neural radiance field based method. I'm very happy to go into details for anybody in like breakout sessions, but the idea is that a volume of stuff exists, not unlike the volume of stuff that we had in the Matryoshka work, except instead of being a discrete shells, it's now a continuous space, right? And we ask a neural network, a multi-layer perceptron, to estimate for any given point in this volume and any particular direction, what is the amount of light coming out, what we call the radiance, and what was the density of the surface. What we called previously alpha or transparency in the Matryoshka model is now this sigma here. Right? So volume of stuff, and we try to estimate at any particular point what the density is, and then also what its color is. When we think about a problem that we could pose with a time of flight sensor, we might also think about how we can exploit other sensors that might be on the camera too. When you have like a connector 0 or something like that, there's also an RGB camera, right? We have a setting that's much more like this. I have some RGB input, I have some time of flight output, from the input from the camera, input from the time of flight sensor, right? And these are mutually beneficial. I can solve classic stereo reconstruction problems using multiple RGB sensors or RGB over time, if the robot is moving. And then I get this time of flight estimate too. And what we're going to say is that the samples from the RGB camera and the time of flight camera must be self-consistent. That if I estimated a depth from the RGB cameras and I took the time of flight depth, it should be the same, right? And then I reconstruct from this volume estimate of the amount of light and the density, what the output images should look like. Right? And then I'm going to pose myself an optimization problem that says, can I minimize the difference of these two to determine what the volume must have been to produce these effects. Okay. One of the nice things about this radiance field approach is that it allows me to solve in a physically based way the light interactions for the light that comes out of the time of flight sensor, hits the scene, and then some portion of that is returned. Let's demonstrate that with a couple of examples. Here's the amplitude returned and the resulting depth from the time of flight sensor. Right? And we're going to use a particular representation of the phase of the returned depth called a phasor. And we're going to use Euler's form, this EI to the theta, to determine that phase of the returned signal. And then A is the amplitude here. And I'm going to visualize that as a classic vector in this amplitude angle space, right, where the amplitude is the length and theta is the direction here. Right? So this is a visualization of the signal that gets returned to the time of flight sensor, right? And depth corresponds to the angle, and then our sort of confidence in the estimate corresponds to the amplitude, how much of that light gets returned. Okay, so as my object moves back and forth in my scene, right, we see that the depth, sometimes I have issues. I'm going to start getting phase wrapping if I go outside of the useful depth range, right? And then the amplitude increases and decreases depending on how far away it is too. Okay, we talked about three cases. The first is the low reflectivity case, where the scene is dark, right? It is just dark, right? And here my phasor is small. In this case, we're going to say that the noise in the estimate won't correlate with the noise in the estimate from the RGB cameras, right? And so I gain robustness from the fact that I get two different samples of the noise that is implicit on the scene, and that helps me reduce the amount of noise for low reflectivity cases. Okay, the second case we talked about was multiple reflections. When I have some piece of glass or something like that in the scene, some of the light's going to reflect through and some of it's going to transmit back, right? And in this case, what we end up with in our phasor representation is like a superposition of the returned light from both of these sources. Right? And that causes me all kinds of problems. I'm sure you've tried to like move a robot around an environment with lots of glass in it, and your time of flight signals are just awful. We're going to try and resolve that for you here too, by splitting apart the superposition. Okay, and then the third case was the phase wrapping. We saw that as the object moves too far away, it starts to look like it's too close. Right? But here, when we add the RGB information too, only one of the true depths is consistent with the RGB values. And so by solving a joint optimization between these two approaches, between RGB and TOF, phase wrapping is automatically solved. Okay. So noise is reduced because I'm using multiple sensors that have different noise profiles. Multipath interference is also reduced because I'm explicitly representing the light that comes from the scenes at different depths through the translucent material, through the glass, for instance, or off the shiny object. And then phase wrapping is resolved because only one of those depths is consistent with both the RGB and the TOF signal. All right, here's our most impressive glass effect result. It's not perfect, but it's not too bad, right? So there's lots of noise on the output here in the left-hand side from the raw TOF signal, and a lot of that noise is reduced, and the resulting volume of stuff has depth that is more closely resembling the true scene because I am explicitly representing how light passes through the transparent material. Okay. All right, so this is really slow, I just want to say. Caveat, it takes like a day to optimize one of these, right? This is not for real time. The other thing you could plausibly use for real time, right? But this you cannot. One of the reasons is that this is a very quickly emerging field. These neural fields, in our case, neural radiance fields to model the time of flight and the RGB light. There's so much work coming out about how to use multi-layer perceptrons to represent useful physical properties of the world that we want to estimate. So we actually wrote a review. There's about 300 or 400 papers on just this area coming out every year, and it's just massively, massively increasing. So we wrote a review. It's called Neural Fields in Visual Computing and Beyond. And Beyond, that's you. So there's like a whole, whoops, wrong slide. Oh, also wrong slide. Here you go. There's a whole section in the review about robotics applications of neural fields. Okay, things like robust estimation for cameras and poses, for objects, for localization, for planning, for things like building affordance maps, for things like avoiding obstacles using signed distance fields or occupancy fields, things like grasp fields, which nobody's really talking about. And it's pretty much up to date with the latest things like this neat Coral submission from Lee and Lee. So please go and check it out. It also has like this Wizzy website where you can go and search for stuff. And then you can also add your own papers too. That's quite neat. To be able to represent very current work in neural fields. I'll also just say that it's moving so fast that like just last month, NVIDIA decided to blow everybody's minds by saying that you could actually do this in just a few seconds instead of a whole day. Right? So if you feel like, James, how am I ever going to use this if it takes such a long time? It's moving so fast that actually you can run this kind of thing online now. And at CVPR this year, there's going to be a SLAM method presented that uses neural fields. This is called Nice SLAM. It was just accepted to CVPR. That uses very, very similar methods to what I described in TURF, with a slightly different construction that makes it significantly faster. Here's the generated depth that they have from their RGB-D camera, and then the generated RGB image. And you get reconstructions that look something like this on the right-hand side. Okay. So this is very impressive from Zhu and colleagues at ETH. All right. how about I pause there? I have a slide that says, is it ready yet? Can I use it? It's kind of too slow, but it's getting really fast. And in just a couple of years, we're going to be using these across the kinds of reconstructions problems that we want to solve. Right? Another use of differentiable rendering that you might think of is that it makes it really easy to build very high quality representations of real world objects offline that you can then use in your pose estimation pipelines, right? If I know the objects ahead of time that I want to be able to manipulate, I can produce very, very high quality representations of them using offline differentiable methods. And they're nice because it's all like physically based, right? They're plausible, unlike learning-based representations, like training from large amounts of data sets, where I have less constraints on what the true output should be. They're plausible because they're physically based, and that's a really useful property for us when we care about the true geometry of things. All right, there you go. I'll stop there. And does anybody have any further questions? Thank you very much. Thanks, everyone.
Yeah, I know the organizers have some questions, at least a couple real quick. Does anyone from the audience have any questions?
Hi, Tom.
Oh, hello. Great talk, by the way.
Thanks.
Does whoever asked, one of the organizers who was the first question, do y'all want to ask that?
Yeah, sure. Yeah, this was mine. And thanks, James. That was such an interesting talk.
Thanks, Michael.
I really loved it. So for those of us interested in implementing these solutions,
Yeah,
especially for me, that first 360 video with the spherical layers, are there any open source or public facing resources to help us VAM-HRI researchers import this work into our own systems at this point?
That's a great question. So we have code out for the deep learning model. We have pre-trained models. We have code for rendering the training data. When it comes to providing a real-time implementation, it gets kind of complicated. We have a version that runs in Unity, and we use like TensorRT to convert the model from the output of TensorFlow, in this case, the pre-trained TensorFlow model, to a particular graphics card, right? But it's specific to a particular graphics card or a particular graphics architecture, and it breaks all the time. A lot of the stuff is still quite brittle when it comes to the real-time implementation. So we haven't yet released that. If people are very interested in this, I'm happy to discuss like exactly what that looks like. But like I had one of my new PhD students just go and look at this, and she was like, "Oh, it doesn't work on this piece of hardware," and then it's kind of disappointing being able to release things that don't quite match up anymore. But yeah, I'm happy to just ping us, and we'll let you know what it looks like to walk through that process. Yeah.
Okay, great. Thank you.
James, I was curious. So in these scene representations, do you have thoughts about incorporating notions of object-based representations into the scene, such as like distinguishing, and how does that kind of play into the whole differentiable rendering kind of component rather than treating it as like a monolithic scene? Yeah.
That's a great question. The easiest answer for that is to say that the way that people are solving objectness is by semantics. And that is sort of okay. It's not perfect, but it's the way that people are solving it right now. So like Andrew Davison at Imperial has a method that does what they call like semantic slam, right? And that will give you back a class for each pixel. It's still not quite there. It's still not really an object, a sense of objectness, right? It's just a sense of semantics. Right? You hope that the geometry reconstruction is sufficiently good that you can then like segment the semantic parts into objects, right? But it's still not quite objectless. So that's the best that I know of that we have right now. There are other people that then take the semantic segmentation and try to do things like fit CAD models and other things to try to enforce more objectness or like better quality reconstructions, especially if you know ahead of time what the object is that you're trying to manipulate, right? Then it becomes this kind of like pseudo pose estimation type problem where you're trying to take the whatever volume of stuff and try and fit the thing that you know that you're looking for. Yeah, but that's as much as I know that we have. Yeah, it's quite easy to integrate semantics into these models. What happens is that instead of just representing, right, on this slide, we said that we had light and density in the field, right? You also then represent a class. So you have like softmax vector over classes in your field, so that each point in the field has some semantic associated here. And you can do that by, there's a couple of ways you can do it. Remember, I need to find the right slide. All right, remember where we have input as RGB and phases, right? You can also have semantics as input, right? And then by the same mechanism, you enforce that you must reconstruct the semantics similarly through the volume. That's the most basic way of doing it.
All right, I think we're coming up on time. I have a really quick question. Zhao, do you want to ask your question really quick?
Yeah, so actually we also noticed the noise problem from those time of flight sensors.
Yeah.
They use a very simple approach like subsampling. So in your work, did you compare your approach with the subsampling, like a really simple baseline approach?
Yeah, we did not. The camera itself, let me just pull up the slide with the aerosol. This one. When you do subsampling or binning, right? Sometimes it's called binning when it comes off the camera. I have a resolution, say it's 640 by 640, and then I get out an image that is 320 by 320, because they take some average or some minimum out of the each of the little 2x2 squares, right? Is that the kind of subsampling that we're talking about?
Yeah.
Yeah. And you see that that's okay in some places. Like it will reduce noise and give you a more robust estimate as long as the samples from any of those 202 regions are still valid or still make some kind of sense, right? And depending on exactly what subsampling function you use, maybe you only need one of those to be valid, right? But it's still not particularly robust. So for instance, all of this noise here on the top of the display would fail from subsampling. All of the pseudo-random noise would fail in a subsampling case. Phase wrapping doesn't really help. Subsampling doesn't really help there either. So subsampling is good. I think we might even subsample ourselves to produce the images that you see here from the TOF sensor. But it doesn't get you all the way.
Yeah, I also see some work they're trying to use geometry cues like those lines in order for the like selected sampling. So yeah, thanks for the answer.
Great. I'd be very happy to talk about that other method and see how it applies here too.
Yeah, thanks.
All right.
All right. Yeah. Thanks, James.
You're welcome.
Yeah, that was great. Do we want to take a break or do we want to just jump right into the lightning talks? Christine, what do you think? I'll throw it to you.
Oh, it becomes my decision. Let's take a 5-minute break and let people get a little bio break in, and then we'll get started at 11:05 or whatever, 5 after the hour, wherever it is where you are.
And if anybody wants to chat, I'll hang around for a bit.
Thanks so much, James.
You're welcome, and thank you very much for inviting me. This was great.
Yeah, James, I actually had a question while everyone else is on break. If you're not going to take a break, how was teleoping the robot? I know you said you'd love to talk about it. How was teleoping the robot with the 360 camera?
Yeah, we managed to. Okay, so the best thing we managed to do so far Steffi Talix was in her apartment in Cambridge, and the robot, it was a Movo, the one that you saw in the slide, was in Providence at Brown, and I think Steffi managed to pick up a ball and put it in the bin. So, very, very sophisticated, dexterous manipulation going on. In terms of appearance, this Matryoshka thing only really gives you enough motion to compensate for any head-sized effects that the user is going through, right? And the reason it works okay is because you're doing it so fast that if the robot's moving or anything like that, you're not storing a map at any place, right? It's really just like a client-side, let's call it a hack, a client-side hack to provide some sig stuff effect for the user. For the robot's general function, and to be able to provide more sophisticated like command and control in the teleoperation setting, you really need a map, right? You need pretty good geometry for the whole.
Oh, I think you muted yourself by accident just now.
Sorry, you need a pretty good map as well, right? And so what we ended up doing was having the classic SLAM reconstruction from a dense RGBD camera as a kind of anchor, I guess, for the Matryoshka representation. So because you only have about this kind of amount of movement, sometimes you really want to step away from where the robot really is and assess the environment, right? And there it's not yet useful. You need to somehow do some additional SLAM on top of the depth that might come out of the Matryoshka system. So yeah, so it was okay. There's certainly a lot more to do, but we managed to get something working into it.
Yeah, thanks. No, I think that's super interesting. And I wonder how many local sets of spheres you to small local planes around you.
Right.
There
was a follow-up from, I can dig out the authors, but I think it was at ACM Multimedia where they infer spheres at multiple different positions, and then they run a CNN-based fuser between the spheres so that you can get some kind of semi-continuous representation. This follows from work that was done at Berkeley in the planar setting. Yeah, that's one way to potentially do it. The other issue that you quickly run into when you move away from using this as just an instantaneous representation, it starts to use a lot of memory. So I have all of these spheres is like a big block of memory, right? And it's super inefficient as a scene representation. So if you're only carrying around one of those that you use constantly just for your real-time adjustment, it's fine. But if you want to start putting spheres densely in the world, it's just incredibly redundant and incredibly expensive in terms of memory.
Cool. Thank you.
Excuse me. You're welcome.
I think we might want to start the lightning talks. Is it starting these off? Michael.
Yeah, I can kick us off. Let me pull up my program here. All right. So these lightning talks, we're going to be aiming for 5 minutes each. I'm just going to remind you when there's around 10 seconds left or so, just to wrap up your presentation so we can keep things moving. Our first presentation will be When and Where Are You Going? A Mixed Reality Framework for Human-Robot Collaboration. Shubham, are you ready to go? If so, you can start sharing your screen.
Am I audible?
Yes, we can hear you.
All right. Okay. So let's start. Can you see the screen?
Yes.
All right. Okay. So hello, everyone. I'm Shubham Sononi. Currently, I'm a PhD student at Interactive Robotics Laboratory at Arizona State University. Today, I will be discussing work in progress mixed reality framework called intention projection for human-robot collaboration tasks. In this talk, I will be going over motivation, brief details of the framework, information about the human subject study setup, and some preliminary results. So the primary motivation behind the designing this framework is to enable safety and predictability in human-robot collaborative tasks. The robot's action may divert as the goal changes. Given this, we want humans to understand robots' actions quickly and adapt accordingly. This can be done by providing explicit visual cues for the robot goals and its workspace. Considering this, we want to finish HRC task efficiently. Thus, we want a framework that can ease the joint execution between humans and robots. Given this, let's talk about the mixed reality setup, which is intention projection in this case. It consists of stereo setup for monocular vision sensor and a projector. Once calibrated, the system provides intrinsic and extrinsic parameters for both projector and vision sensor. This information is basically used to do the projection mapping. Given the goal pose with respect to camera frame, we can visualize different renderings onto the projector frame in the form of warped image. In addition to real-world objects, simulated objects can be visualized on 3D plane in real-world setting. So let's talk about the human subject study design for this framework. This study aims to perform generic sorting tasks in collaboration with the robot, where robot will sort heavy objects, where human will sort the lightweight objects. In the first part, human will be given information in the form of the pattern table on the 2D display. In the second part, while using intention projection framework, we incorporate two fundamental modes to provide explicit information to the human. First mode is called shadow mode, and this mode provides information about robot's current trajectory and workspace. Here's the user performing a sorting task using shadow mode. Here we provide delay of 0.2 seconds between projection and robot's execution. In this case, users still use information about the pattern from the display screen. Here we can see that the trajectory information helps human to adapt sorting task accordingly. Now, in the intention projection, second mode is called highlight mode. This mode provides discrete information by highlighting goals object for humans and robot. Here's the user performing sorting tasks using the highlight mode. Here we highlight the robot goal object using the red color and the human's goal object using the green color. Finally, we use the combination of both shadow and highlight mode called dual mode, and here's the user performing the sorting task using dual mode. Now let's discuss about the human subject study measures. Here we use raw NASA TLX and multidimensional mutual trust measures to test the user performance in different modes. Currently, we have performed experiments on 12 different users, and I will go over few key results. For the NASA TLX, it was found that the mental load was lowest in dual mode, while shadow mode itself was mentally demanding compared to the highlight mode. In terms of frustration level, it was found that the shadow and dual mode contribute to lower frustration. On the other hand, highlight mode does not provide instantaneous information about robot's trajectory. Thus, there is a higher frustration level. In terms of effort, on average, dual mode provides most A's in the task performance compared to the other modes. And now in the MDNT case, it was found that the shadow mode was more reliable compared to the highlight mode and was at the similar level to the dual mode. Thus, we can infer that continuous information provides more system reliability compared to the discrete information. Finally, I would like to get feedback about the current study design, possible future studies, and comparison against possible baseline frameworks. Thank you, and looking forward to talking to you in the Q&A session.
Great, thank you. Next up, we have Chow, investigating explainable human-robot interaction with augmented reality. So go ahead and share your screen whenever you're ready.
It's actually Anna.
Oh, I'm sorry.
Yeah. Can you see my screen and hear me
Yes.
okay?
Yep, we can hear you and see it.
Just start. Okay. Thank you very much. So hello, everybody. My name is Anna Blardinelli, and I'm with the Honda Research Institute Europe, together with my co-author, Chao Wang. And I'd like to briefly show you today our efforts to introduce explainable AI cues in human-robot interaction, in particular in the context of learning by demonstration. So during learning by demonstration of physical tasks, the robot needs to follow the relevant paths of the tutor's demonstration. And current approaches often implicitly assume a unidirectional transfer of knowledge from tutor to learner, but that actually is very much the case that the learner feedback can influence and shape the tutor's demonstration. And by nature, the tutors is anyway concerned with representing the mental state of the interaction partner. Still, in HRI, this cannot happen the way we are used to among humans. So here, for example, in a purely language-based interaction, the tutor wants to teach a skill and must first find out what the robot knows about an action and if it can even see the plate in the scene. So recently, Tellman and Zinke introduced the perception attribution problem in the context of explainable robotics. That means that a person's judgment of what a robot knows about a particular state of affairs X in the environment depends on uncertain estimates of the robot's capability to perceive and understand. So not knowing what a robot knows about the environment may give rise to uncertainties about our own action when interacting with a robot. So as a solution to these issues, we design intuitive cues that can explain to the user the current robot's understanding by making use of augmented reality and HoloLens capabilities. We target here semantic learning, where a robot needs to collect two types of information: the sequence of actions to complete a certain task and the change of state in an object due to a certain action. And at the same time, it needs to make the user aware of what it knows and understands in the scene in front of him. So we envision three types of XAI cues. First, object-related information that shows the recognition of an object and of its current state, and at the same time shows the attention of the robot in the scene. Action-related information that shows the recognized action of the teacher, and reasoning or supplementary information. At this time, there is no learning taking place. So for example, we could show the recollection of the observed sequence. And here in a mock-up implementation, you can get the feeling of having at least the object labels displayed through the HoloLens as the robot observes the demonstration. In this case, for example, toasting a slice of bread in the toaster. So we propose to validate these cues in a user study to answer the following research questions. Can XAI cues improve the teaching by demonstration experience with respect to other modalities? And here we propose as comparison gaze cueing and joint attention, which have been tackled extensively in HRI. And we ask further whether a combination of modalities is better than just XAI. So we would manipulate the feedback modality by having either the robot gazing to and mentioning objects in the scene as the user does its demonstration, or in a second condition, make just use of XAI cues in AR, but no other feedback from the robot, while the third condition would combine the first two. And for task variability, we picked up 3 different kitchen tasks. And our hypotheses are that XAI would improve the user experience in terms of effectiveness, coordination, and users' awareness of the robot state. And further, that combining XAI with other feedback modalities further improves the performance. And we can have different combinations in our setup of virtual robot and holograms, or real robot and holograms, or real robot and augmented objects, for example. So social learning processes are made of both social moments where partners can engage and exchange instructions and feedback, and teaching moments where the actual task is demonstrating. And depending on such context, the robot should behave differently. So we designed a finite state machine which detects and weights the current cues coming from the user and determines how the robot reacts. For example, in the idle context, the robot chooses just by itself anything to focus on, Whereas as this user approaches and looks at the robot, it moves to a social context where the robot returns the gaze or shows something in the XAI bubble, or in a teaching context when the user is actually doing the demonstration, the robot can converge with its gaze on the scene or showing the corresponding labels. Oops, sorry. So to sum up, we are shown our proposal for XAI design elements in HRI during learning by demonstration, and we are currently in the process of implementing the cue detection and robot interaction behavior, and plan next to conduct a pilot and a user study. And in this sense, your feedback would be very much appreciated. Thank you.
Great, thank you. All right, move along here. We have Tobias Keller. Go ahead and share your screen.
Yeah, one moment. So you should now see it. Oops.
Yeah, we can see it.
Okay, then hello everybody. My name is Tobias Keller. I'm a PhD student from the Technical University in Cologne in Germany, and I'm presenting today my work together with Frederick Götze about a study concept we have developed about an RR robot motion intent communication in collaborative assembly. And so therefore, I first tell you something about the background. We started from the Me Robot project, which you can see on the right, where we built a collaborative assembly cell where you build up sensor cases together with a robot, and it is adaptive because it reacts to the determined stress level, and then it changes the speed and other modes. And we're using this initial setup for our follow-up project, MultiPsy, which means a multimodal immersive learning with artificial intelligence for psychomotor skills. And we are doing it in the field of AR-assisted learning of the interaction with a collaborative robot. And what is our motivation behind that? Yeah, as Wisniewski et al. Said, robots' actions must be transparent and comprehensible for efficient human-robot collaboration, so that the human is able to anticipate robots' actions. And this is becoming more and more important in increasingly flexible collaboration. So when robots can make actions on their own and we have flexible task allocation, then it's more important to understand what the robot does. And other related work has shown that AR visualizations have a positive effect on robot motion intent communication, so that they understand the robot better and they feel also safe, and yeah, the whole situation is more understandable for the person. In our research, we want to conduct next, we want to apply two of these approaches to a different setup and one self-developed application, and we want to compare them. So at first, the adjusted setup. Here you can see also the Yumi robot we used, and now we're changing it to a robot handover task, where the robot takes objects from the side with the two different arms and has 10 different object handover points, so that the person who is working with the robot doesn't know where the object is given from the robot. And we want to randomize the arms which the robot take, and also the sequence of the different handover points. And yeah, we're using also the Microsoft HoloLens for the visualization. Then next, the concepts we want to take. First, the one from Grünefeld et al. They call it volume visualization, and they project a colored cylinder onto the robot's motion joints. And it was the original intention was to prevent collisions when you are in the red zone. And we want to transfer it to object transfers. The second one is based on Newberry et al. It's a wireframe visualization. They used it to show where a human has to place an object so that the robot can take it. And we want to use the same visualization for the robot to show where he's going to give the object to the human. And one self-developed approach where we use symbols and short texts, which show which arm is going to be used, and also the time when the robot starts to give things to the human. And what do we want to do with it? We have developed a study design concept where we want to, yeah, how many? Sorry.
30.
Sorry, okay. So we want to have a laboratory study with a within subject design, and the independent variable is the presentation, the RF presentation. And we measure the time and use partially standardized questionnaires, as seen before, the Nasatel X, raw Nasatel X, the Godspeed 1 and 5, and the newer human-robot interaction evaluation scale. And next, the future development, we want to further develop the study design and also the visualizations, integrate hopefully the feedback from the workshop, and then conduct the study and hopefully derive implications as results from the results for ARQs and AR robot human object handovers. And thanks for your attention.
Great, thank you for the talk. Next, we have Matthew Lubers. Go ahead and start whenever you're ready.
Great, thanks, Michael. Just a second. All right, so I'm Matt, and I'll be presenting today along with my co-author, Akib Tabrez, on augmented reality-based explainable AI strategies for establishing appropriate reliance and trust in human-robot teaming. So let's say we've got a human trying to perform a navigation task in an uncertain environment, and they'd like to improve their performance by adding a robot teammate to the mix who can help them explore that environment and collapse its uncertainty. This is tricky in practice because in these types of environments, plans are inherently unpredictable and constantly changing, and optimal performance can't be achieved without coordinated adaptive plans, a problem which becomes doubly important when the task is time pressured, like with search and rescue. This type of coordination is wholly dependent on live and efficient communication between all of the agents. So that inspired our research question, which is how should autonomous systems communicate with human teammates in time-sensitive, uncertain environments? To address that question, we developed MARS, a min-entropy algorithm for robot-supplied suggestions, in a paper set to be presented at AMOS this May. The core of the algorithm is characterizing environmental uncertainty by a shared dynamically updating probability mass function, or PMF, which can be used as a reward function to solve parallel Markov decision processes via online RL for both human and robot teammates to optimize a joint policy. The robot takes actions as they're given by Mars, while the human is shown generated action suggestions and or environment data delivered via an AR headset. So the AR guidance comes in two flavors, which correspond to the two data products of Mars. Action recommendations form the basis of prescriptive guidance, where the human teammate is shown arrows and pins corresponding to directly suggested actions, while environment data in the form of that PMF informs descriptive guidance, which shows an evolving heat map and acts as a decision support tool for the human. These pictures come from our experimental domain, where participants played a 3D AR-based game inspired by Minesweeper, alongside a drone teammate who possesses a noisy sensor to provide data to help the human diffuse a number of mines hidden throughout boxes. So in the experiment, we varied what type of AR guidance we provided to the participant, either prescriptive, descriptive, or a combination of both. And long story short, the combination of both guidance types performed better than either prescriptive or descriptive alone on measures of trust, interpretability, and time to solve. And it also allowed human collaborators to act more independently, choosing for themselves when to follow or ignore the arrow-based suggestions they were given.
From our user study and results, we found some insights into new obstacles. And from here on, we will highlight some of them along with the potential solution. First, we had the intuition that prescriptive guidance would lead to system one thinking where people are in automatic mode, whereas a descriptive guidance would lead to system two thinking characterized by conscious and effortful decision making. And by combining both of this concept, we wanted to have a balance of cognitive load, which we saw to an extent in our experiment. But we also know from the prior research that people subconsciously shift towards system one thinking over the period of time. Therefore, our first overarching design goal is to investigate whether we can nudge people towards system one or system two thinking based on the uncertainty in the environment such that we can proactively avoid getting into failures. Secondly, we noticed that some people overtrusted the guidance, accepting the bad advice, and some people undertrusted it, ignoring the good advice. Ideally, we want human teammates to accept high quality advice and reject low quality advice. Therefore, our second overarching goal is to investigate how we can appropriately steer user trust by communicating the quality of advice. To solve these questions, we will leverage explainable AI techniques to achieve our goals. One technique is counterfactual explanation. Counterfactual explanation refers to suites of techniques where specific changes to the input of a known models are identified and that lead to changes in output classification. For example, if we ask the classifier why the image in the left is an auklet rather than a cormorant, it would find the region in the left image that needs to be swapped with the region on the right image to be classified as cormorant. Now we can use the similar idea within our domain by highlighting the specific change in the region, showing the old and the new reward under the specified point to explain why there is a sudden path change or some unexpected advice from the system as shown here. We can build on this counterfactual technique by using justification to explain the rationale behind the given advice. Previous research has shown that the robots are perceived as more helpful, intelligent, and trustworthy when they provide the underlying rationale. And this can be used to mitigate negative impacts from sudden path change. So here is the example of our justification design, where we leverage the visual counterfactual alerts and combine it with the semantic justification for any potential confusing advice given by the system. This type of explanation achieves three goals: assesses the system's confidence, provides spatial location of the change, and how the change has happened. Prior work has shown that if explanations are overused, it can increase the workload and lead to habituation. So our key insight here is that by strategically leveraging justification only during the actionable changes, such as sudden path change, we can avoid saturation of explanation while taking the benefit of the justification. With this, I would like to end our presentation and thank you all for your time, and we look forward to talking with you all in the breakout session.
Awesome. Thank you, Matt and Akib. Next up, we have Gregory. Go ahead and share whenever you're ready.
So hello, everyone. My name is Gregory VAM-HRI. I'm a master's student at the Human Robot Interaction Lab at the University of Massachusetts Lowell. And today I'll be presenting our design for a user study to compare a 2D and VR human-in-the-loop planning interface for controlling a mobile manipulator robot. We're working together with a team from Northeastern University, which spun off from one of the competitors at the DARPA Robotics Challenge. In the DARPA Robotics Challenge, teams would compete to complete a variety of complex tasks using a humanoid robot. And we had previously presented our VR interface at VAM-HRI 2021. The team at Northeastern University has also designed a 2D keyboard and mouse interface, which is designed to be a simplified version of several of the interfaces used at the DARPA Robotics Challenge. So here you can see the robot visualization in both of our interfaces, along with the point cloud and the camera streams. Additionally, operators can set waypoints for the robot to follow. These, for example, here you can see these light blue manipulation waypoints. Then the operator can command the robot to plan a trajectory through these waypoints, which it communicates, shown here through this ghost robot. Both interfaces provide the same information and are capable of achieving the same actions to complete tasks. However, we allowed the interfaces to vary in ways that made intuitive sense, given the strengths and weaknesses of control methods found in VR and keyboard and mouse interfaces. For example, to take advantage of the ability to work in 3 dimensions, the operator can control the robot's head by reaching into the virtual robot's head, pressing their grip button, and then dragging a marker to the location that they'd like the robot to look at. This method is fast, simple, and makes sense for the VR task space. In the keyboard and mouse interface, the operator can drag sliders to command the robot to look up, down, left, and right. And forcing this action to have been completed in the 3D interaction window in the middle would have made this action unnecessarily complex. A table detailing the ways that each of our interfaces conveys information and the planning actions can be seen in our paper. To compare VR and 2D interfaces, we have designed a 2x2x3 mixed study design, where participants will be assigned to either the VR or 2D keyboard and mouse condition, and then they'll complete a navigation and manipulation task, and they'll complete 3 trials of each task. In the manipulation task, participants will be tasked with commanding the robot to pick up blocks and to place the blocks in this partially completed tower in the center here, with their goal being to recreate the tower shown in the bottom right of this image. Participants will gain points for each block that they successfully pick up, and for each block that they successfully place in the tower in the center. They will lose points for each collision with the environment. In the navigation task, participants will command the robot to drive to 3 navigation goals. And while they're commanding the robot to drive to these goals, they'll have to ensure that the robot avoids 3 obstacles that can be seen here in the environment: the wet floor sign, the traffic cone, and the toolbox. We have 3 sets of obstacle locations, 1 for each trial that we'll use in the study. And once the robot has reached a navigation goal, the participant will have to adjust the robot's height in order to view the Land-Alt-C visual acuity test and the buckets. They will gain points for each correctly reported test, and they will lose points for each collision with the environment. This work was motivated by a set of 4 hypotheses. First, we hypothesized that the VR interface will be more usable than the 2D interface, and we'll measure this through the system usability scale. We also hypothesized that participants who complete tasks using VR will report less workload compared to those in 2D. We'll measure this with the NASA TLX and the gas tank questionnaire. Additionally, we hypothesized that participants who use the VR interface will develop higher levels of situation awareness compared to 2D. This will be measured through interruption questions that we'll ask during the navigation task. And then we hypothesized that participants will have a higher rate of improvement in the VR condition compared to 2D, which will be measured through completion time and planning time. And finally, we hypothesized that there will be fewer collisions with the environment and that participants will have, on average, higher task scores in VR compared to 2D. We'd appreciate any feedback on our study design, and we'd be happy to answer any questions during the breakout session. Thank you.
Great, thank you. Our next talk will be given by Phaedra. Go ahead and share your screen whenever you're ready.
Can you see my screen?
Yes, yeah, we're good.
Okay, so hello everyone. My name is Phaedra Curlin, and I am here with Madeline Muniz, Mason Bell, Alexis Muniz, and Jack Burns from the University of Colorado Boulder. And I am presenting our lab's work on developing a virtual reality digital twin and environment for troubleshooting lunar-based infrastructure assembly failures. So we are motivated by NASA's goal to create a sustainable presence on the lunar surface, and this will include the deployment of the Lunar Gateway, which will provide low latency communications with the lunar surface. This will also consist of autonomous robotic missions like the Farside Radio Astronomy Array, where in the case a rover enters a state of failure during such autonomous assembly missions, we would have a local teleoperator which will need to recover the rover. So current methods for troubleshooting rovers include using a full engineering hardware twin of the rover in the Mars Yard, which is a physical recreation of the Martian environment on Earth. This method is not portable, is time consuming, and still has inaccuracies in the rover and environmental emulation. So by using novel technologies that have become more accessible, such as stereoscopic cameras, which can be placed on the rover to scan the environment, and virtual and augmented reality, we propose a virtual reality platform in which teleoperators interact with a digital twin of the rover in a simulation of its environment. This platform is risk-free, can replicate different gravities, provide multiple copies of the robot, and is portable. In the VR platform, the operator uses the same controls for the rover as with the real one and has the ability to adopt the egocentric view, which is the image in the bottom left, and the exocentric point of view, which is the image in the bottom right. So for our design process in creating the digital twin, we started off with the CAD model used for the physical rover, which generates the collision model. It is then brought into Blender to apply textures and exported to the format required by Unity, which is our VR platform's game engine. Finally, we imported it into Unity using the Unity Robotics Hub URDF importer and attached the appropriate ROS controllers used by the physical rover. So our experiment is still in the development phase, and well, we propose a baseline experiment in which we would evaluate whether the use of a VR platform is more effective than using none at all for rover recoveries. And to address this, we have come up with a task in which the teleoperator would have to realign antennae that were misaligned during deployment. The operator will be carrying out the same realignment task in the virtual and physical environment. And as such, there will be two groups in the experiment, one that is exposed to the VR environment and one that isn't. We will be issuing surveys to measure the operator's situational awareness, cognitive load, as well as the system usability of the VR platform. We will also be looking at the time it takes for the operator to execute the task in the VR and physical world, the number of times they reset the virtual world in case they make a mistake, and the number of times, the number of tries it takes for them to realign each of the antennae. But before our experiment, we will first evaluate how representative the digital twin and its environment are of the actual rover and the experiment room. We will measure key aspects of the rover to calibrate our digital twin to those of the physical rover. And so the first one is the latency of the ROS messages being sent to the rover. So if the measured latency is longer for the physical one, we will implement a delay into the digital rover's messages to match those of the physical one. The second aspect that we will investigate is the absolute joint error. This will take into account how precise the movement of the robotic arm is compared to the expected values that are inputted into ROS. Thirdly, we will compare the joint movement resolution, which consists in moving one of the joints by the smallest possible value and compare it to the expected value. And finally, we will look at the errors associated with driving, which can occur due to wheel slippage and the torque being applied to the motors. So in the short term, we will be looking into the equivalency of our digital rover to that of the physical rover using the measures that we presented. We will also be developing surveys based on the current best practices to measure the situational awareness and cognitive load of the teleoperator, as well as the system usability of our VR platform. And we will finally run a pilot test to expose some of the overlooked flaws of our experimental design. In the long term, we would like to evaluate the use of a physical twin for troubleshooting, like what is done with the physical duplicates in the Mars yard, as opposed to our digital twin. And finally, we would greatly appreciate feedback on our metrics, specifically those regarding evaluating the accuracy of our digital twin and its environment, as well as for our experimental design. Thank you for listening.
Great. Thank you, Petra. And we have our last paper with Kali. So go ahead and share whenever you're ready.
Okay, can everyone see my screen?
Yes.
Perfect. All right. Hi, everyone. I'm very happy to be here today to talk about our recent work of the topics towards robust exocentric mobile robots teleoperation in mixed reality. This is the joint work between the Dutch electron synchrotron and the human-computer interaction group at the University of Hamburg. My co-author are my co-supervisor, Reinhard Bacher, Wim Liemens, and Professor Frank Steinecker. So some of the background of this work at DAISY, the short abbreviation for Dutch electron synchrotron, there are several large-scale physics facilities like the particle accelerator. In these accelerators, it is normally highly radioactive environments that are inaccessible for human. Therefore, using mobile robot for facility maintenance and inspection is a very attractive solution. However, this largest facility, as you can see from the video, has very complex and very non-robot friendly environments. I'm not just talking about the corridor which robot can pass through freely, but also under this accelerator tube that under this, like where the robot could be sent for expecting the electricity or the radioactive level, which is very difficult for the conventional immersive robot telepresence methods to see, as they sometimes have limited field of view, or it is very difficult to facilitate autonomous motion in such a large scale remote environment. Therefore, we would like to use an approach to combine the existing digital twin of the accelerator and immersive stereoscopic video stream from the remote. As you can see from this figure, we have remote video stream that's overlaid on top of the digital twin of the remote environment. This way that the operator's sense of presence in the virtual reality will not be completely broken. However, the user could also use an extracentric perspective to plan future movement or tasks of the robots. Next, we would like to we designed how we could perform extracentric operation of the remote robots, because as we know, like the remote robots is inaccessible, and it's the resource for on-site experiments limited. We instead use toy robots as example and develop an open source design space for studying using mixed reality, virtual reality, or augmented reality to operate a mobile robot. As you can see, this system supports multi-use XR backend and supports multiple platforms such as HoloLens 2 or the Oculus Quest 2 with the video pass-through, or we can also run it virtually directly in the Quest 2. And we will make the code available after some days. And we for the user study, we designed two major interaction techniques. One is by raycast pointing, which we define a series of waypoints, and the robot execute these waypoints one by one by turning and moving in a straight line. And the second one is to for the operator to draft robot's routes by using an intuitive freehand drawing in the air method. And future work, we would like to evaluate our extracentric teleoperation and telepresence method with the conventional egocentric MR telepresence system, also with keyboard to the screen. We would like to evaluate the system usability scale, the operator's operation workload, task completion time and task completion success rate. In addition, we would like to gain expert feedbacks from the robot operators from those high energy particle accelerators and perform semi-structured interviews. What I would like to learn and discuss from this workshop from you is like we have this very nice digital twin environments that we have the general structure of the accelerator, and I would like to learn how would be the community standards for performing HRI study inside of digital twin, and how to evaluate and compare this result with the real robots. And in addition, as the previous talk also mentioned, how to compare the virtual robots behavior with the real robot behavior. Here, thank you so much for your attention, and I look forward to the discussion in the Q&A section.
All right, thank you. Okay, so for the next portion of the workshop, we are going to break out into breakout rooms. This will be the first of 2 breakout sessions like this. Please refer to the program, which I just linked in chat, to see which papers will be in which breakout session. So authors of those papers, please move to those breakout sessions that you're assigned to. And then for the rest of us, feel free to enter any breakout room that's interesting to you. And then we will reconvene at, looks like 10:20 Pacific time for our next session of Lightning Talks. Okay, I think now's a good time just to get things started so we can stay on track with our schedule. So our first paper will be by Padraig Higgins. So go ahead and share your screen whenever you're ready. And just like the last time, we'll have 5 minutes and I'll just let you know when you're running short on time.
Okay, that's just a second. Okay, everyone see the presentation?
Yes.
Okay. So my name is Padraig Higgins, and I will be presenting our work, the head pose as a proxy for gaze in virtual reality. And this is work I did alongside Brian Barron with Cynthia Matusik. Okay. So just to get started, so motivation. I think our work primarily revolves around language grounding. So it's kind of learning what language means in the physical environment. So this kind of requires large amounts of data, and that can be costly to acquire. And to do this, we've been looking to simulation to help. So kind of some of the goals of this is just extend the reach of our data collection beyond kind of the physical laboratory, kind of ideally to kind of anyone, anywhere with a VR headset. And then kind of even in simulation, and still have the need to potentially do manual labeling, kind of linking like descriptions of objects to the actual object in the scene. So kind of the question we are asking is, can attributes of the human-robot interaction be used to label data during the data collection? And kind of in particular, what can we learn like purely from body language? Okay. So kind of to do this, we kind of use the river simulator, which we presented here last year. So it's just kind of a combination of Unity and ROS, with Unity kind of providing all the user interface and capturing all their interactions of like the head pose, the hand pose, and audio, and then also generating all the like visual percepts for the robot. And then just ROS is controls the robot and is doing all the sensory kind of processing, and it's all connected with together with ROS Sharp. Okay. So in the experiment we ran, we just have a Unity scene that was kind of reused from the AI2Thor, and we have a robot in the scene, and it's just kind of pointing at various objects and then prompting the user for descriptions. And then the user can just use the hand controller to start and stop the recordings. Okay. So then to determine like what the user is looking at, we have the head pose from SteamVR and Unity, and we have like point clouds of each of the objects in the scene, like from ROS. So then for each of those points, we just calculate the angular distance between like the gaze vector and the point, and we assume that the smallest angle is the target of the gaze. And just so the results for one of the participants we ran through. So kind of you can see here, the blue bars is the ground truth of which object they were actually describing during that like audio sample. And as you can see, kind of works fairly well for like the bread, lettuce, and apple, tomato, and bowl, but performed very poorly for mug. And just kind of the actual numbers to go along with it. So as you can see, that for everyone has kind of had the same sort of performance with not performing well on mug. And kind of our takeaways were that the larger, less slightly clustered objects were the ones that performed better. And then just kind of going forward, kind of hope to integrate this work with actual learning language and about objects from their descriptions and interactions, and then kind of repeat the same experiment with kind of the physical robot in the real world. And then also kind of using more complex gaze models. And I think there's been a work with Bayesian inference and hidden Markov models. And I think that would be some of the places that we'd be interested in feedback. So yeah, I think that's everything. Thanks for your time.
Great. Thanks, Patrick. Our next paper is by Eric Rosen.
Sharing.
Actually, Shri will be giving the talk.
Oh, great. Whenever you're ready, Shri.
All right. Can you guys see my screen?
Yeah.
Awesome. All right. Hey, everyone. My name is Shri. I'm a student at Brown University, and today I'll be presenting our paper, Learning Robot Motor Skills with Mixed Reality. So teaching robot motor skills is hard, and it's hard for a few reasons. So first, tasks in the real world are complex. And as a result, learning needs to be sample efficient to reduce the teaching burden by humans. Second, robot movements must be safe and constrained to prevent unpredictable and potentially dangerous actions. Third, agents trained with one goal in mind should be able to adapt and solve new tasks, even if the goal is modified slightly. And fourth, tasks rarely consist of a single skill. Decomposition of a task into multiple skills is important for learning. It's much more difficult to learn a single policy than learn policies for individual skills and then chain them together. And lastly, robots don't operate in a vacuum. They need to be able to infer the position and orientation of objects in the scene in order to instantiate new frames of reference. So in our proposal, we're going to identify world knowledge that's useful for learning motor skills. We'll enable a human to convey this world knowledge with mixed reality. And we also have a motor skill learning approach for leveraging all types of world knowledge. We define the following 4 types of world knowledge that's useful for learning. The first one is motion trajectories. So for example, this might consist of a data set of teleoperated rollouts using an MR controller. We also have task constraints, such as, for example, in the diagram at the right, you can define a 3D boundary of space where the robot cannot enter. Planning representations might be for example, creating subskills by segmenting motion trajectories. And lastly, we have object information, which involves specifying object poses in the workspace and defining motor skill frame of references. So now I'm going to go over the details behind the core learning algorithm in our framework, the CDMP. Our paper focuses on the peg and hole insertion task. So in this task, the KUKA arm, which is pictured on the left, needs to motion plan a peg attached to its end effector into a hole on the workspace. The task requires generalization in the sense that the hole location varies from rollout to rollout, but it also requires an adherence to constraints in order to stay within a safe area of the workspace. So what is a DMP and what is a CDMP? A DMP is essentially a PD controller with a custom forcing function F. F is a function of scaled kernels, allowing it to trace out intricate paths while still giving us the nice convergence guarantees of a standard PD controller. The DMP is a function of a set of kernel weights, which can be learned using off-the-shelf methods like locally weighted regression. And a CDMP is just adding an additional residual weight learned for the forcing function that's optimized at inference time to guarantee satisfaction with respect to the constraints. So we collected a set of demonstration trajectories from the peg and hole task, and we treat each degree of freedom independently with a fitted CDMP controlling it. So here we have shown the X, Y, and Z coordinates from the end effector in Cartesian space. And once trained, the DMP is stable for new settings with guaranteed convergence. So looking ahead, we hope to design the MR interface, allowing users to specify task constraints. We also plan on conducting a user study investigating the ease with which teachers can communicate constraints to the agent. Thank you.
Yes, excellent. Thank you. Next paper up, we have Jonas. Let's see.
All
Paper.
right.
Oh, great.
All right.
Okay.
Can you hear me?
Yes, I can hear you.
All right. Hello, everyone. My name is Jonas Takara. Today, I'm going to present the research work we are working on foveated rendering for immersive remote telerobotics. And as you know, I mean, everyone is here working in telerobotics, and I don't think I need to put a lot of presentation for remote telerobotics. But just to give you a highlight, we are working in the remotely teleoperated robots. So this is basically useful for explosions, or when there is a disaster. It could be like the pandemics that we have now, and we want to maintain, contain, and also inspect these kind of situations. So an effective implementation in this field in telerobotics would benefits lives in the frontline workers, basically. So these are some of the applications we are working on in the lab. We have monocular video feedback, point clouds rendered inside VR, and then the operator will try to do some such tasks. So one of the examples that I'm going to show you today is this remote teleoperation project. So on this one, we wanted to display an RGBD or a point cloud inside virtual reality device, and then an operator will try to like put this chunk of wood into a target place. But doing such kind of tasks, it's somehow difficult, because the user is looking at the monocular or stereoscopic video feedback and then the depth map on the side. And we, on this project especially, we were like putting this wood into a target, but actually the wood is black, and the wood chunk that we have in VR is somehow white. So it's not really completely replicating and showing the exact situation. So for this reason, we would like to replicate exactly what the environment is. And we did 3D reconstruction for that. But the 3D reconstructed environment is big in size, and it needs large bandwidth, and then also low latency. So having this latency and low resolution, it's basically impacting the user. And so it also provokes cyber sickness. So for these problems regarding especially bandwidth and latency, we are proposing this paper that I'm going to present here. So what we would like to do is we wanted to exploit the user, how the user is looking at, or the human visual system basically. And we have the highest quality acuity in the 5 degrees, and then this high quality, it falls towards to the periphery actually. So this can be modeled as minimum angle of resolution that basically models the properties of the human visual system. So we put this formulation together with the optical system of the human eye inside virtual reality to sample point clouds, basically partition, sample, and stream the point clouds into the master station. So in the remote side, we will have a 3D constructed environment that we will stream to the master station. And from the master side, we will take the fixation point of the operator and then send it back to the remote side. And then here we will partition, sample, and stream it back to the operator for visualization. So the partition part is done like this, and then each partition or each region is assigned by different voxel size, and then they are approximated by their centroid point for to reduce the requirements needed. So we did several experiments actually on this one. This is the video that I'm going to show you that we did. And also we did subjective and non-objective evaluation on the work. So we have three some kind of experimental conditions, and we compare them with the reference one. So objectively, we measure the bandwidth and the latency improvements that we can get from there, and it shows that it's improving a lot. And also we did the subjective study, basically the quality of experience regarding using this setup. And it's showing actually somehow a very good quality, you know. With this, I will conclude. Thank you so much. And if you have some comments and feedbacks, I would like to hear it later. Thank you.
Thank you. Great talk. Our next paper will be by David Pulji. So whenever you're ready, feel free to share your screen.
I still need permission.
Oh, Jonas, do you mind stopping sharing your screen? Sorry.
Yeah, but I think where is it? I couldn't see it actually. I don't
Oh,
know
no
why.
problem. Let's see.
Can you?
I think I can do it. There you go.
All right, perfect. Sorry.
Oh, no problem.
All right.
How about, is that working for you now, David?
Yeah, should work.
Great.
Perfect. So my name is Ed Pulis. I will present a paper that I have done with Alexandru Vasilace and Michael Mende and my professor Bjorn Hein about inside-out infrared marker tracking. So first of all, a bit of motivation. So at our lab, we actually previously developed a lot of marker track or infrared markers equipped tools that we usually track them with outside sensors. So that was all and good, but then the marker or the tracking systems got a bit old and it was bound just a single setup. There are other papers that did, a lot of other papers that did similar things with marker-based tools. So here are just the three from Gaschler, Leutred, and Reinhardt. And all these tools are actually quite useful, especially for inputting trajectory on surfaces and digitalizing surfaces into 3D representations. However, they are bound to specific setups, and we don't like things to be bound since we have HoloLenses and we would like to move freely from robot cell to robot cell. So we were thinking, can we do the tracking inside out using the HoloLens? So we tried first if the markers were visible, since we have a depth sensor on the HoloLens and it emits infrared light, and indeed the markers are visible. And then we started, okay, can we track the markers? So we divided the job, we divided the problem into 3 jobs that can be run on different threads. So the main job here is the computing job, which actually detects the infrared blobs, does a threshold, and we use a region of interest to basically reduce the search area. We map the 2D positions to a 3D position since you know the camera parameters, and then we basically just match the markers to the model and try to detect the rotation and translation in the HoloLens coordinates. Then the prediction jobs, and this is not that fast. We just basically do linear interpolation of position and quaternions, and a streamer job is purely for communication with the PC. And why I mentioned HoloLens coordinates, because we also have a referencing step that I will not be talking about here. That's basically then referencing everything into robot coordinate system, and that's running on the PC itself. So just how does it look like in practice? So basically, that is how we see the markers. We distort first the image. We detect the blobs. As I said, we use the region of interest from previous steps to make the search a bit faster. We do a fast model matching, and then basically we are trying to do a least square method to actually detect the rotation matrix and the translation vector. And then finally, we then get a marker tracking inside the robot cell, but without the need of any external sensors. So everything purely on the HoloLens. The experiments were not that good, but as I said, everything is running on the HoloLens still. So in a static case where we left the HoloLens and the tool itself static, we got a precision of under 2 millimeters for position and under a degree for rotation. But as soon as we started moving the HoloLens and the tool, the performance dropped significantly. And very nice here to see is how the position and rotation in the static case is non-Gaussian, because it's basically mostly due to IMU drift. While in the dynamic case, then you can see a nice Gaussian because of basically multiple sources of tracking that the HoloLens uses are activated. But basically we got our proof of concept. So here I'll just show a nice video while I talk about the feedback that I would like. So basically, how useful is our tools in regards to other input methods? For example, we have input by hand now that is working quite well. We have hologram weights and so on that we can use. Is it better to use other tracking solutions like visual markers, or just drop markers entirely and use deep learning methods? Any suggestions on how to improve precision? And finally, we have done this with the HoloLens 1. So if anybody has any experience or intuition, if HoloLens 2 would do a better job, then I would really much like the feedback on that part also. And that is all from my side.
Thank you for the talk.
My pleasure.
Our next paper is going to be by IPEC. Sorry if I said that wrong.
No worries. Hi, my
Karen,
name
you'll
is
be presenting. Okay.
Hi, I'm Karen, and our paper is on augmented reality appendages for robots, design considerations and recommendations for maximizing social and functional perception. Before we dive deeper into what our paper is about, we want to define and clarify some key concepts. We talk about social perception, which is the user's belief that a robot is capable of participating in the interaction as a social actor that is interactive, autonomous, and adaptable agent that performs anthropomorphic actions. We also talk about functional perception, which we define as the user's belief that a robot is able to accurately communicate its functional capabilities and intentions. In our design recommendations, we talk about dietic gesturings, which are gestures that point to an object or area in order to redirect the user's attention. We also suggest anthropomorphic gesturing, which are human-like gestures that support HRI. We also mentioned non-anthropomorphic gesturing, as seen in the middle photo, which are abstract gestures like virtual arrows that help communicate the goal of the action accurately and efficiently.
AR visualizations have been used in VAM-HRI to enhance robot expressivity and improve user perception of robots, despite limitations of gestural capabilities in physical robots. For instance, in the study shown above, AR robot extensions were used to perform social gestures on a low expressivity robot, increasing its social presence. AR visualizations can also be used to increase functional perceptions of robots. For instance, research has shown that non-anthropomorphic gestures can be used to boost the accuracy and efficiency within an interaction. However, both anthropomorphic and non-anthropomorphic gesture systems have been found to involve trade-offs between functional task performance and usual social perception of robots, creating a need for a unified approach that considers both functional and social attributes.
Our paper seeks to answer the following research question. Can we develop a system of design recommendations for AR appendages that maximize social and functional perception? Through our background research, we compiled a list of design considerations and proposed design recommendations based on those considerations. The first consideration that we propose is the motivation of the action. So does the action have a functional component? Do we want to prioritize accuracy and efficiency? Or does it have a social component? Do you want the robot to seem more human-like, or does it have both? The second category that we propose is visibility. Basically, is the target object and the robot in the same AR field of view? We then mentioned saliency, which is the target object easily distinguishable from its environment and surrounding objects. Lastly, we propose distance, more specifically the distance between the target object and the robot. So is the target close to the robot, or is it farther away?
In order to summarize how our design recommendations connect to our design considerations, we compose the table in front of you. So as you can see, we list different intersections of our design considerations, and then we give recommendations for anthropomorphic gesturing indicated by A, non-anthropomorphic gesturing indicated by NA. We also recommend combinations of both of them in certain situations where the gesture system placed first should be prioritized. And then we created a special recommendation of directional non-anthropomorphic gesturing indicated with an asterisk after NA, where the user can simply look at the gesture and identify the target object without having to look back at the robot. And we recommend using this gesture system when neither the robot or the target are in the frame of view. In the future, we would love to further investigate our design recommendations and conduct an empirical evaluation, as well as explore various anthropomorphic and non-anthropomorphic gesture types and look into the specific salience of the gestures we're recommending, as well as apply our design recommendations to our own personal projects in order to benefit from both functional and social perception. We'd also love to leave you with some key takeaways from today. So we developed recommendations in order to maximize social and functional perception in non-robot gesturing, and we did this by composing the following design considerations, which are motivation, visibility, salience, and distance. We then provided a recommendation depending on these considerations of anthropomorphic, non-anthropomorphic, or a combination of both anthropomorphic or non-anthropomorphic gesturing.
We would appreciate any feedback on the design recommendations that we put forth in this paper, along with any overlooked design considerations that we didn't include in the paper. We'd also appreciate any advice or tips on how we can go about testing these design recommendations that we put in our paper.
We would love to thank our research team as well as the National Science Foundation and USC Viterbi for funding our research. And we will be happy to answer all of your questions in the breakout room. And here's our key takeaways for reference. Thank you.
Thank you. Our second last presentation will be by Zhao Han. So whenever you're ready, feel free to share.
Okay. Can you hear me and also see the slide?
I can hear you. The slide might still be loading. Oh, there it is. Yep.
Okay,
Feel free to start.
now. Hello, everyone. I'm Zhao Han from the Colorado School of Math. Today, I'm going to present our work towards the understanding of physical versus virtual robot appendage design. So the motivation is that in HRI, people have studied a number of interaction patterns extensively. For example, the arm movements, gestures, and eye gaze. However, they all require physical components, such as a physical arm or a physical head. For physically limited robots, as you can see on the right, they can't really benefit from those interaction patterns that are proven. With AR or MR, it allows virtual appendage. So we can add a virtual arm or a virtual head. However, are those virtual appendage better than physical components? So in the literature, HRI has studied the virtual agents on screen versus robots, and they found that the embodied physical presence is premier, both subjectively and objectively. For the AR and HCI field people, they also studied the virtual human, as you can see on the right, and they found actually they're not that bad. So people perceive them as physically distant and also has a higher social presence. So there is a contradiction here for the screen agents and the AR agents. So what about the AR robot appendage? So they're kind of partially virtual. So a robot designer may have the question, should we add an AR or real arm to my physically limited robot? So if the AR arms are better, there's really no need for real robot arms, which are costly and unsafe for nonverbal communication. And also, as you can see, for the QR robot, it's really hard to mount an arm onto that robot. So we are certainly contributing new knowledge on virtuality of a robot arm, but there is a potential confound, the reality match. For example, as you can see here, a physical robot with either an AR arm or physical arm can point at the physical reference. So if we find some effect, we can probably say it's just because the reality match between physical arm and the physical reference. So it's unclear about the play of the virtuality factor of the task objects, which are really examining the reality match or mismatch. So here we added the AR reference. So the physical robot with an AR arm or physical arm can also point at AR reference. So to investigate all those, we designed an experiment where the task is for a mobile robot to point at a sphere, and the experiment follows a 2x2 between subjects design. So as you can see on the right, we have the arm virtuality as well as the reference virtuality. So a physical robot with a virtual arm can either point at physical objects or the virtual objects. And we can also have a virtual arm pointing at a physical object or a virtual object. So our hardware includes a Turtlebot 2 and a VidoX arm. And for the virtual arm, we have the CAD models from the VidoX arm to render it, as you can see here. And for the reference, we place them on arc, so they're all within the field of view of the HoloLens 2. And there are 45 degrees between each other, and we have 3 balls distance from the robot to the reference. And we also plan to have 1 meter between the participants to the middle ball. So we have 3 hypotheses here. The first one is we believe equivalent accuracy for all conditions. So this one will be measured by participants air typing the targets. And secondly, we believe that reality alignment mediates efficiency, which is measured by the reaction time, which will implement it using the iRacking API from the HoloLens tool and add the invisible objects at reference locations. So for the reality mismatch, we believe there will be equivalent efficiency. And if there is a reality mismatch, it will increase the time for participants to identify the targets. And thirdly, we believe that reality mediates perception. And if there is a reality mismatch, it will reduce the perceived naturality and likability, which is measured by the social presence, anthropomorphism, likability, warmth, and competence. So here are 3 takeaways. So the first one, physical limited robots, they can't really use those nonverbal methods. So can we use AR virtual robot appendage? It may not be better than the physical ones. So our plan is to compare AR and the physical arm in AR and the physical environment. Any feedback and question is welcome. And we also have like an AR work in the short contribution section. So we'll see you there.
Awesome. Thank you.
Thanks.
All right. Our final paper before our second breakout session will be by Ian.
Hello. So I am Horatio Yuxinghan, and I will be presenting in behalf of our collaborative group. Okay. Let me share my screen. All right. Thank you, Michael, and thanks for offering us the chance to share our collaborative group's prototype and the design research work. In the past few years, Ian, Karthik, Aaron, and we basically noticed and realized the design opportunity around the telepresence platform. So as the need and implementation of telepresence platform growth, we have found a limited design attention that's been given to the form factors. Typically, the form factors comes as either a stationary mounted display, a tablet-style screen on a mobile platform, or most recently, headsets or individual like headgears to support AR or VR implementation. However, all these form factor has limitation in supporting a dynamic and equal collaborations or interactions that require immersive and embodiments. And as a result, our group set forward to prototype a family of platforms that exploring the immersive and embodiment telepresence experiences by exploring the form factors and how we can introduce in the mixed reality application into it. And here are the 2 examples that we have prototyped: the large screen mobile telepresence robot and a mixed reality windows. So I'm gonna kind of dive in to talk about these 2 prototypes. So what you're seeing now is the large screen mobile telepresence robot. And in this specific prototype, what we're trying to do is projecting a full-scale human image, allowing the remote participant to have a better embodiment. What it does allow us is, you can see that we're trying to creating an as equal and a natural interaction, because you're projecting the remote user almost full scale as human, which is a very what humans are used to in terms of interactions. And the full scale vertical screen also allows the remote presenters to have to use a full range of their body language. And these are just short videos that showing out some of the prototypes and the experiences that we're trying to envision. So next is the second prototype that we were exploring, which we call a mixed reality window. So what you're seeing now is we have a dual screen with camera mounted on both sides. What this markup creates is a fully pass-through effect, which means so users on both sides or objects on both sides can be seen from both sides, and the screens allows us to overlay additional virtual content on top of it. In terms of user scenarios, for the first large screen mobile telepresence robot, we were envisioning there is going to be a collaborative or a classroom environment where these type of machines would allow instructors or presenters to use their body language and giving a kind of detailed instructions. And we also see in a more speculative kind of use case that there's the robot itself has a lot of potential of creating a more engaging and a more emotional communication. Thus, it could have a lot of potential in supporting older adults. For imagine that if you have an older family members living in assisted homes and assisted communities, you can establish a more engaging communication by projecting yourself full scale in front of them. And the nature of the mobility platforms allows you to actually engaging with family members who has a bit more limited mobility issue. So these are the scenarios that we're imagining for the mixed reality window, which will envision that could be used in, again, a classroom or highly collaborative environment, which allows to have collaborators on both sides of the screen, and passing through the screen, which you can see is the remote participant can actually be projected full scale onto the screen as if on both sides. The on-site participant are actually seeing and experiencing the remote participant in the same room. On top of that, because of the screen nature, we are allowing augmented and virtual aspect and elements to be projected. Imagine so the notes or questions that can be projected on top of the real life feed of both users. And for the specific for the mixed reality window, we also see a more speculative use case where it can be used for a kind of either classroom or museum setting, where imagine that a scientist, a researcher from a remote site who doesn't have a full setup of tools that allow them to be like, either be presented as AR, VR, but a simple camera can allow them to project themselves into a museum and has a face-to-face interactions with students and pupils. So for the next steps, what we're looking for is prototyping, basically bring the mixed reality window into larger scale, which is closer to what we envision in this kind of collaborative and the museum use case. And we're planning to basically enlarge the size of the prototype that we have built and using that as the platform to explore both use cases as well as what type of AR and VR UX that we can implement on top of the screen. In terms of feedbacks, what we would like to get from the group would be thinking about what are the additional possible user scenarios that these type of large screen platform that we can benefit from. And also in terms of headset gears, AR and VR, they also support immersive and embodiment telepresence experiences. But what are the differentiating features and use cases that a physical robot have over them? And what are the collaborative features that our platform can work together with VR or AR headset? All right, thank you very much. And unfortunately, I have a hard stop after this, so I couldn't participate the breakout, but feel free to reach out any of us on our paper and share your thoughts and feedback. Thank you very much.
Thank you. And thanks again for all the speakers in our second session. At this moment, we are going to move into our second round of breakout discussions. So as before, if the authors can take a look at the program and move into your respective breakout sessions, the rest of us feel free to join whichever sessions are interesting to you. And we'll meet back up at 11:30 Pacific time to reconvene as a group. All right, see you then. So welcome to our group discussion session before we wrap up the workshop. But quickly, I want to pass off to Tom Williams, who's going to quickly share about a VAM-HRI virtual design element taxonomy that he, myself, and a few other VAM-HRI workshop co-founders have been working on. So with that, I'll pass it to you, Tom.
Yeah, sure. So very briefly, because then I need to, hopefully there are other people on this call also who in a little bit will need to drive down to University of Denver for the watch party we're having here. I need to go a little early because apparently I'm ostensibly helping organize it, even though I'm not from University of Denver. But over the past couple years, Dan Safer and I, and my student Tao and Dan's student Michael, and then Tadagata Chakraborty have been working to try to make sense of all of the great work that's been going on in this area. I think one of the nice things about this area is that there's so much work that's coming. There's so many people working on it. That's why like the very first year we ran the workshop, we had like 70 people. The downside is that it's a lot of work coming out very quickly, and people don't tend to use the same terminology and so forth. And so right after the first workshop, we had this effort where we tried to design an initial sort of framework for categorizing things. This was like the interaction cube, this sort of like three-dimensional framework for reasoning about things. We then decided to work together to try to build out and flesh out something maybe a little bit more coherent and useful. And so over the past like 2.5 years, we've been working on this more comprehensive framework. We just put it out on arXiv with a survey paper with a taxonomy of all this type of work that's been being done like in this workshop and the surrounding fields over the past 30 years or something, right? One of the I think really cool things about this is that because Tadagata works at IBM, he was able to use IBM's cool some of their platforms they have there to create some nice visualizations for how all these things fit together. Moreover, what this, and Michael just linked to it, and the really important part for everybody here is like the survey only goes up through 2019 because we had to cut things off at a certain point and be like, no, we're not adding anything else to the survey. Stop. As part of that like IBM platform, it provides the opportunity for people to basically make pull requests to try to add their request that new things be added in to the taxonomy. So we would really appreciate, again, we put it up on arXiv. We're hoping to send it to maybe, Frontiers or something soon. Before we did that, because this is really, we view it as sort of a community effort and growing out of this particular workshop series. We would really appreciate feedback from people about the particular categories that are used, but also we'd like to use this as an opportunity to ask people, like if there's stuff that work of yours that you would like to have listed in there, before it gets really submitted, or if you have contentions about how things were categorized, to please submit pull requests and make sure that it's reflecting a state of the field that everybody in this community can sort of agree on. That good, Michael?
Yeah, that's great. That's perfect.
All right.
Thank you.
Thanks for running a great workshop. I'm going to go drive down to DU now. Thanks, everyone.
Hey, drive safe. Okay, and with that, let's begin our group discussion. So here we can talk about some major themes that were discussed in the breakout sessions, maybe questions that the breakout sessions wanted to pose to the larger group. I can begin actually. So the first breakout session that I was part of had to do with digital twins of robots and digital twins of environments that real robots are in. So these linked real world and virtual settings. And a common question that came up that the authors and myself were kind of curious about was what level of realism, whether it's the recreation of the virtual environment or even the physics of how the robot interacts with the environment, is acceptable for running a VAM-HRI study, where we can say that these results may mimic ones we'd find in the real world, rather than just a virtual setting. So I'd like to open the floor to discussion on that, or if anyone has any insights on that.
Perfect one-to-one. Joe, you can talk. I'm just making a joke.
Okay, so I think the realism is very important. So actually read a paper for a virtual human trying to pass physical walls, and that didn't perceived very well from participants. So I believe that the physics must be respected. So yeah, that's my thought.
I have an additional question. On top of that is in terms of safety aspect, realism in terms of safety aspect. Because if you do a simulation, but if there are a little bit of offset in some hazardous situation, this could lead to very bad consequences. And I was wondering if any work that what is the state of the art of ensuring robot safety, when presenting simulation virtually, and when it is when the instruction is given to the real robot.
Does anyone know the state of the art in this area? I have some thoughts, but I have thoughts about everything.
Go ahead,
I do not. No, I do not know the state of the art. I think one of the interesting things, kind of flip it the other way, is if you're doing simulation, you're doing training, at the end of the day, it's actually a good thing to allow for a catastrophic event, because if you're training, you'd rather happen, obviously, in VR, AR, whatever, as opposed to the real world. And in a way, you might want tighter tolerances in VR so that in the real world, you do get a little bit of that leeway, in a real sense. Robot safety, I know, is a whole massive subfield in physical robot world. I know nothing about it, but I think that would be a really interesting place to explore. Yeah, that's all I had.
Thank you.
Yeah, can I add one thing more? All right, so maybe I can talk about remote teleoperation. So in this case, we want to control the robot, right? So there are these two things that I see in this field. So the operator need to perceive high quality, or it should be a faster communication, no? So it depends on the task on these things. So for example, if the task is to search for a thing or to inspect, so at this point it needs to have a higher representation of the remote environment, so high quality. But if the task is to track something in real time, or to find something at a certain time, they need to be a lower resolution. It means we are not going to have a higher representation of that environment, but it will be a lower but a faster communication. No? So I think I would say it's that task is dependent on teleoperation tasks. Thanks.
One thing sorry. One thing I'll also say about safety is with simulation versus real life is maybe what is being learned or trained in simulation and then being transferred to real life can have an impact on how safe it is in the resulting setting. So what I mean by that is if you train a robot to do some task like pick and place or any kind of motor skill or something in simulation, and you're training a neural network to maybe map like where the pose of the robot was in simulation, there's no guarantee that in real life potentially that it will not run into things in the real environment, because you're kind of just, you're giving very low level control about how the robot should move. But maybe what you're actually training in simulation, even though you're maybe teleoperating the robot to do some pick and place task, is estimate what the intended object is to be picked up. And then some sort of safe low level controller can actually execute that task. And so in that setting, you can learn, you can teach in a VR environment and still guarantee that whatever is being inferred or learned safely transfers to the real environment, because you're putting a lot of the work on making sure that the underlying algorithms and policies are safe inherently. So you can still use things that have guarantees and stability, so that in the real environments, they even in virtual environments, whatever was learned and trained satisfies those in the real environment.
Thank you so much.
Want to move to another session's questions or thoughts? Anyone have another session's questions or thoughts?
I was kind of curious what you guys were talking about in the virtual alterations section. Like, it seems like most people were there, but for those of us that wasn't, like, could you give like a brief summary maybe? Or
yeah, Matt, do you want to give a brief summary?
Yeah, I can. Yeah, it was great. We talked about all sorts of stuff. Let's see, I wrote down some notes. I guess I'll divide it into two chunks. First of all, there was a lot of discussion about, or some discussion at least, about how to do virtual alterations or indicators, or I guess I'll say annotations for referring to virtual things versus referring to physical things. Or it was also divided into when you're doing doing something that's task-based versus more social, and how we might want to use different kinds of annotations, or in this case, like alterations of the robot's body or what have you. So like an example there was, like, you might want to use a non-anthropomorphic design to do more task-based things. Like maybe you just like draw a circle around the thing that the robot's going to do. But if you're doing something more social, then maybe the robot like gestures, because you're trying to also have the robot be like transmit all this social information. We then also talked a lot about all different kinds of alterations and augmentations. I wrote down a list, like older work that involves putting like an animated character on top of like a Roomba or another mobile robot that doesn't have much expressivity to it, just like literally having like a humanoid character sitting on top of the robot that can express all this stuff. And then also smaller alterations, like having a tail on a Roomba, or putting wings on a robot, or this was partly sprouted by, we were talking about the fur hat robot, and how maybe a body could be added to a head, instead of, we've mostly been talking about like adding an arm to a body, or like adding a head to some arms maybe. But we kind of like flipped that script, and we're like, well, what if you like had a robot that was just one small part of a body, but then you add like a whole bunch of additional virtual body to it that would have all this expressivity. And that kind of sparked the final part of our discussion, which is about like potential unintended consequences of these different representations, and like what all they might communicate that may or may not be intended by the designers, and maybe how that plays in. Those are at least the things that like occurred to me as most interesting. So obviously there's probably some other stuff that I didn't write down.
That was a great summary. Thank you.
Yeah, so it felt very wide open. Like a lot of these things have, like even the examples where there's been some work, like putting a virtual character on top of a mobile robot, it seems like there's there's just a ton of possibilities there to be trying out.
Yeah. One that's kind of along that same line, like, well, making that taxonomy that Tom was briefly mentioned about, it kind of helped point out in the virtual alteration space things that haven't been done as much. One of which being virtual diminishments, or where the robot disappears up with occlusion. There's one work by Plopsky et al., I believe, where they make the robot arm invisible to help a teleoperation. But we usually haven't seen too much of that. And I think that's probably going to be something that'll kind of grow kind of in the inverse sense of these alterations. And then another thing I didn't see as much was like special effects alterations. Like maybe we add lights, or maybe like sparkles or something to the robot. Maybe that makes it more like attention grabbing, maybe for educational settings or whatnot. But that's just a couple random things that come to mind.
Something that was occurring to me as you both were talking is, I don't know if I'm probably like dating myself here, but like paper dolls. So like you can put different like clothes on this, like the paper doll, and like dress it in different ways. And so like, dressing a robot, and how might the color, or if you put a different, like you were talking about tail and wings and things like that, but also just like a t-shirt or a cape, or all these other things that might change how we perceive them. And that would be really, I think, well, easy in some ways to do in AR or VR. Yeah, I don't know, that's just something that occurred to me as you both were talking.
Ooh, someone linked Euro linked a pretty good paper, making sets of app dresses for robotic movement. I have a really quick thing, and then Euro, I don't know if you want to talk about that paper, but that was almost my PhD, Christine, actually, about customizing how robots look for young students to get some ownership over your learning environment. And I think another interesting thing along Michael's line too is we talk a lot about like having these visualizations, and obviously there's a bunch of saliency things, and I think dynamic salient appendages and stuff is gonna be super interesting. I make a red arrow. Okay, well, the stuff behind it might be red, and then you can't see. And also, do you want to see the stuff behind that? And those should likely be more dynamic, as opposed to I choose a rainbow color, and then that's because I want rainbow in my paper at some point. But yeah, I don't know if you want to talk or if someone else had something too.
I'm not. I just thought of that paper when you talked about dressing up robots, but I was thinking like this made me think like about and this might be opening like a bunch of different topics, but this dressing up robots is for kind of physically programming them and visually programming. And I was thinking like, has there been, like, I'm not aware if there's been any work on dressing up virtual robots and programming them in a sense by doing that. And doing like the same thing that this paper from 2010 was doing, but like in a virtual setting, maybe you could paint the robot and like make it behave in different ways. Yeah, it was just ideating.
Yeah, if you have people that want to do that, that has been an undergraduate project that has been in the back of my head for 4 years now, and I have just continually pushed it off. So I think that's a great space to explore. I think it's super exciting. And then you can go along, like, there's a ton of papers about designing, especially with kids, like robots and stuff like that. And it's a lot easier in a way because you don't have any physical constraints.
Yeah, cool. We can, if I find any students, I'll let you know. we can make that happen.
I was trying to remember a paper. For the life of me, I can't remember its name. I'm gonna keep looking, but where it's kind of along the same vein of, instead of dressing up a robot, they change the texture to communicate like whether or not you want to touch it or approach it or not. Like maybe give it some like a cosmetic alteration. Like you're not changing its form or adding appendages, but you change the texture and maybe you give it like fur. Maybe a kid like want to touch it. Or the other thing they had is kind of extreme, but it was like a magma texture. So like don't touch it. But yeah, you can communicate these like approach, don't approach type interactions with changing the robot's skin.
Yeah, I think that's very interesting for safety, right? If you some robot, real robot may harm you, you can probably put some texture there to show like, okay, here is very dangerous.
Yeah, and
go ahead.
Yeah, I think AR has like a lot of potential in making these things, enabling these live metamorphosis of these robots, which would be very, very cool to explore.
So I'll bring up something that we discussed in the first breakout room that I was part of. Some folks were asking, and I don't know that this exists on like a large scale. If there's some sort of comprehensive list of like different instruments and scales that are used for, you know, measuring whatever in any of your studies. So a place you could go and find out, you know, if these are the kinds of things I want to measure, maybe it's, you know, how likable a robot is, or, you know, how sociable it is, you know, what are my options for scales to use, particularly for VAM applications. But I mean, yeah, I didn't have a good answer for that, and I'm curious if anyone here has one.
Are you going to create one, Christine, and add it to the VAM-HRI website? And then I would be greatly, yeah, I'd be greatly appreciative if someone would do that. Or else it's, yeah, hobbled back together to a wiki that is 10 years out of date.
Right.
It'd be an interesting, I was going to say the only other thing, it'd be an interesting thing even to crowdsource it, like a workshop or a future tutorial or something of like just measures and then just compile them, especially if they're validated or not, because that ends up being a lot of the issues. And yeah, you don't need validated scales, just make up your own. I'm sure Matt loves that comment. Matt is very...
Matt has unmuted his microphone. I was actually, I don't know, you might have spoken to this a little bit, Christine, because I only I was looking at some diminished reality stuff and was distracted. But like, I have been thinking throughout this workshop that like a lot of this stuff is super new and like I was saying earlier, like if you put a agent on a room, like a virtual agent on a Roomba or something, I feel like about 10,000 things happen to the user, such that like, I guess if you have a task where you're like really specifically interested in some like performance metric, which could be a social performance metric, like how creeped out are they, or do they think the robot is intelligent or something like that, then maybe that like allows us to like choose our quantitative metric and like try to develop a scale for it. But a lot of this stuff seems so open-ended, where it's like, how do people respond to there being a tail on a robot? Like, I would be tempted to move towards qualitative methods at first. And I don't have much more to say than that. I haven't thought about like, I guess it would depend what the thing is in terms of how you would explore, right? But I did kind of feel sometimes in some of the presentations where there was like a very specific hypothesis that it was maybe prematurely narrowing it down to like is it comparable to this, or is it more than this on this metric? When I'm like I don't even, I have no concept for how people experience this qualitatively. I don't know. I guess I'm trying to say not just qualitative, but I would be more exploratory, is a better way of putting it, I think, and asking broader research questions for some of this stuff. That's my personal opinion. And is not really a direct response to you, Christine, as just something that had been on my mind. What's that, Tom?
But I need a graph for my paper or it won't get accepted. I
Yeah,
can't do
so
qualitative.
that is a
qualitative analysis takes a
cultural
long.
problem.
Yeah.
Yes, if you want to get it accepted to HRI, that's its own difficulty.
Oh, I don't want to get into that. But yeah, I +1 to the qualitative. That's come up in another workshop where we're doing robot tutors of like qualitative was the most useful in the real world. Like when you do interviews, you get the most feedback and the teachers tell you a ton of stuff. And then it's like inverted as like that quantitative survey data gives you like the paper, even though like, I don't know, I'm super opinionated.
Oh, you're saying in your study, the most interesting results you got were from the interview, not from the
like,
survey you ran. Yeah.
I want to improve this thing. Why don't I just ask the people what they thought of it? And then as opposed to, oh, take this survey and then fill it out, poke some stuff.
Right.
Oh, look, we got bigger number here than number here.
Yeah, what does that even mean?
About
Yeah.
this at all. Sorry.
Sounds like we have the fodder for another workshop.
Yeah, maybe it'd be great to get some folks with qualitative research expertise connected, like in this space, connected with the people with the technical abilities to like make these annotations and overlays happening, and some graphics people and some HCI design people. And that might be like a research collaboration construction thing. Like do we have all the right types of expertises in the room to do this kind of research? Maybe we're lacking some qualitative methods folks to help us. Like once we have the cool tool, we're like, oh, we want to put an arm on a robot. This could do so many things, but like someone to help us, like when we do the user study, actually learn a bunch of stuff that we didn't actually suspect before the user study, right? Not just that, like proving that it is not a terrible idea or better than not having an arm on the robot or whatever, but like learning some stuff that no one knew before. That would be incredible, a technical and empirical contribution.
I usually do that by adding a free form question after like your maybe 1 to 7 scale. So if you have time, you analyze it. But if you, because we only like have 8 pages for HRI, and for workshops, we have probably 2 to 4 pages. So sometimes you just can't put them in. Like I see a lot of qualitative like research in the HCI conference. That's because they don't have like 8-page limit. But when you see those papers, you kind of will probably just wait to read it because it's like 12 pages, right? So like there are kind of balances between those two. So if you have more than 8 pages, you can put more content, but then maybe less people will try to read it because it's like an hour commitment, things like that. Yeah.
I mean, I would argue that it's not necessarily a page limit thing. It's what is valued, you know, what has historically been valued.
Yeah, HRI is kind of, I mean, it's kind of a subfield of HCI, but they just push all the HCI stuff away and do our own stuff. So I see a lot of like the experiment design papers. I mean, HCI like this, that's already been mature, but here is like something new. So I feel like there's something wrong, but I guess HRI is like a unique context. So those are still contributions.
Well, on that note, we are nearing the end. Is there anything that anyone else wanted to share? Some highlights from any of the breakouts, things that stood out to you, last questions that you didn't get to ask?
In case anyone was wondering if the field is growing, here is, I did a Google Scholar search for basically VAM-HRI. It's more complicated than that slightly, but the number of publications is the Y and the X is the year. So the top 1,000 results of Googling for VAM-HRI here is the graph. So it's definitely growing. And also, if you are interested in helping organize this workshop so that you can help this, what is it, nascent? Do you have to say the word nascent, right? Or whatever it is, nascent field, which is not growing field. Please reach out to us. We're looking for new organizers for next year, especially. So, yeah.
And please feel free to continue to use the Slack workspace to discuss any of the papers, answer some questions. I saw some questions have been posted, some were answered. I think there's still some that are outstanding. Yeah, feel free to continue to use that. That's just an ongoing workspace. We reuse the same workspace every year. So you're welcome to use that as you wish. Thank you all for coming. I don't know if any of my co-organizers want to say any last words, but yeah, I thank you all for being here and for making this a great workshop yet again. And I'm looking forward to seeing hopefully most of you at the main HRI conference.